Okay, this is lecture 10. We're redoing it for the people that are in quarantine. Um, Review sessions, we haven't been doing them lately because nobody seems interested. Lab last Thursday was preserving feeds. If you weren't at those um, labs, see me about a makeup. We'll get things there. The exams associated with this class, we've got the October 1st, first exam, feed ID, October 22nd, second exam, October 5th, lab practical, November 19th, and our third exam will be in December during our abbreviated finals week. So in this lecture, we talked about how do you calculate dry matter intake. We talked about why it's important, what influences it, how do we calculate it. So calculating dry matter intake. We need 5 things to get the job done. We need the weight of the feed, the dry matter percentage of that feed, the weight of the feed refused, the dry matter percentage of that refused feed, and the number of cows. Implied in this is we're doing this on a daily basis. So dry matter intake, DMI, as pounds per cow per day is the standard that we're dealing with. So calculating DMI, dry matter intake, we need to figure out how much was eaten by those cows, and we'll say in a 24-hour period. You could do it any way you wanted or whatever is appropriate, but 24-hour period is more or less a standard. So we're going to expand that eaten out, and we're going to assume that the difference between the fed or feed offered and the feed refused is eaten. So we know what we gave to that group of cows. We know what was left over. We can assume that what's the difference is what's been eaten by the cows, and then we can divide that by the number of cows. To figure out the specific dry matter, we need to take our fed pounds, multiply by its dry matter percentage, and then we need to subtract the feed refused pounds multiplied by the refused dry matter percentage. And then we take that consumption, dry matter pounds consumed by the group of animals, and we divide it by the number. So here you can see the 5 different numbers that we need in the appropriate arrangement to calculate dry matter intake. So we need to think about or look about, with these 5 factors, these 5 things, which ones are easy and which ones are hard to get a handle on. So if we're looking at dry matter intake, we need good scales. And if we have those, the fed pounds should be easy. We know what we're delivering to a pen. We also should be able to get a fed dry matter percentage. Either we can do a dry matter on our TMR, our total mixed ration, the feed that we offer the animals, or we can take, given the feed ingredients, we mix it the way we're supposed to, we can come up with a calculated dry matter of the feed that's offered. And this is usually good enough to get the job done. The refused and the refused dry matter are a lot more complicated to get a handle on. It's hard to figure out sometimes how much feed is there accurately. It's hard to get it onto a scale. That may be the physical act of collecting all that feed up, having, if we do it with a skid steer, something to push against so it all goes into the bucket, and then getting that material back into like a mixer wagon. Maybe our skid loader isn't tall enough, or we have to do a lot of walking to get that done. We have to move the skid loader over, walk back, get the tractor. So there can be a challenge there. Also, the dry matter percentage used can be a challenge as well. We know that the feed can dry out on a hot summer day. We know wet and rainy, it may collect water. So the dry matter may change over the course of a day. The challenge with that is we'd have to go for every pen, do a separate dry matter, and we just don't have time for that. So what we usually do is we usually make some assumptions, and I'll get to that in a second. The number of cows in a group can be pretty easy, like if there's a constant number there, or we can pull things off of our computer programs, Dairy Comp, AFI Lab, or we might have something like a freshening pen where the animals are constantly coming and going, and knowing in a 24-hour period how many animals were in that pen on average, that can be a challenge. So what do we need to get the job done? We absolutely need the fed pounds. If we don't have scales accurate enough to give us that information, there's no point in calculating dry matter intake. We should be able to, if we have accurate weights, to get a calculated dry matter percent based on how much of each feed that you put in. If we know the dry matter of each feed, which we do up at the dairy, we should be able to calculate that dry matter percentage, or we can go into the computer program and it will make that calculation for us. If we're adding this much as fed, we know how much dry matter is in each of those tons of feed, we should be able to sort out and figure out our dry matter percentage. We can make assumptions about refused pounds and refused dry matter. Not getting those perfect is not going to have a profound effect on our final dry matter intake. So we usually estimate those. We do, up at the dairy, we do get those weighed, but we have a system where that can get done. But if you can't get that done, estimating those, taking a look at it, guessing what's there, can be good enough. And then we absolutely need the number of cows that were in that group. If we don't have that, there's really no point in doing dry matter intake. So that ends our discussion specifically about dry matter intake. We're going to move on. We're going to spend some more time still on the defining animals part of our science of nutrition. And we're going to specifically look at what animals do and how do they use the dry matter, how do they use the nutrients, and what do they do, where do they need nutrients for. So again, we look at our Morrisville cow and what it consumes. We've got dry matter, 55 pounds, say in our pen 4 cows, and that'll include 10 pounds of crude protein, 10 or 24 pounds of non-fiber carbohydrate, 17 pounds of neutral detergent fiber, about 2 pounds of ash, and about 2 pounds of fat. What is she going to take those nutrients and what will she do with them? We're going to have 4 different categories that we're going to talk about. We're going to talk about maintenance, which is basically living and not doing much else. And then we're going to add other things to it. So building something, whether the animal's growing, fattening, reproducing, making wool, we're adding biological tissue in some way, shape, or form to the body. We'll talk about making a product, specifically looking at lactation and making eggs. And we're going to talk about movement, whether that be for work with draft horses or play, say, with goats. They're very active, and accounting for that is semi-necessary. So getting back to these, maintenance, the physiological state where an animal is not particularly active, not gaining or losing weight, not producing anything. So just being or maintaining the self. when we think about nutrients, maintenance is absolutely always the first priority. We take care of those needs first, and then if we have anything left over, we can do one of the other three. So maintenance is going to be about maintaining the body tissue, maintaining that warm-blooded constant temperature, maintaining the vital body processes, and maintaining water balance. There's a lot of energy associated with making sure all the electrolytes are where they're supposed to and that the water is where it's supposed to be. When we calculate our maintenance requirement, it's a function of body size. So the equation for our cattle is body weight to the 3/4 power. And this equation holds up over a range of species. So as an animal gets bigger, the maintenance requirement goes up, but it doesn't go up linearly. It goes curvilinear and it's got a little drop down. So the bigger the animal is on a per weight basis, you're going to have less needed per pound of body weight as the animal gets bigger. When we think about maintenance, we've got a range of the percentage of the nutrients that are absorbed that go to this function. So cattle will use 90 to 20% of their nutrients absorbed for maintenance. If we're thinking about what a growing animal eats, about 50% of what she eats is going to go toward maintenance, the other toward growing. If we have a mature cow that's not really doing much, we might have 90% of her consumption. Think about like early dry period, late lactation, very late lactation, not producing much. You might have 90% of the calorie and nutrient intakes are going to go toward maintenance. If we have a high producing dairy cow producing more than 100 pounds of milk per day, only 20% of her calorie and nutrient intake is going to end up going toward maintenance. And this is where we get the phrase 4 times maintenance. She's got 20% of her intake, particularly energy, going toward her maintenance, and then 80% is going toward milk production. So that 80% is 4 times what the maintenance requirement would be. So maintenance, always first, always the first priority. When we start to balance rations, we're going to put numbers on that. So one of the things we can say that the body is building something. So we mentioned already growth. We're building muscle tissue, bone, any of the connective tissue that goes with that. Maybe we're fattening those animals up. We're marbling the meat, adding layers of fat, adding layers of protein that are going to mark that animal getting ready for market. We may be building the next generation. A pregnancy needs nutrients to build and grow. That fetus has got to go up to 80 or 90 pounds for a Holstein by the time it calves. Wool for sheep is a very significant protein outlay, so we have to account for that. The technical term associated with this is tissue accretion. So we're grading tissue, we're making them bigger, greater quantity. If we compare an animal to what their diet would look like at maintenance versus if they are building something, how does that diet change? You're probably going to have increased intake, particularly in an immature animal. The more they grow, the more you're going to eat. You're going to have increased nutrients needed, and the nutrients needed go up faster than the intake. So you're going to have increased nutrient concentrations associated with animals that are building something. So versus a maintenance diet, it's going to be higher in protein on a percentage basis, higher on a caloric basis and megacalories per pound. So a higher concentration associated with that diet. The second thing we'll talk about is making a product. So eggs, milk, I'm going to call this biotransfer. We're taking protein, we're taking fats that are absorbed in the digestive tract. They are on the condition of that animal, and they might be transferred to the udder and then placed in the milk and the egg um, to support that animal wherever it is, either the calf um, drinking the milk or the egg that has to provide all the nutrients in that little package to build a chick. So egg yolk is the perfect amount of materials to make a small chick. So we're doing that. We're going to have increased intake. Usually we're talking about a mature animal here, reproductively mature. We're going to definitely have increased nutrients. We need a whole lot of things to create the milk, to create the eggs. And again, the nutrient amounts go up faster than the intake. So we have increased nutrient requirements, nutrient concentrations in our feeds. So higher in protein, higher in energy, higher in fat. These making a product are generally the most efficient. We're transferring stuff from one place to another, and there's an energetic efficiency associated with that. The third thing we'll talk about is lots of movement. So draft horses pulling things, horses running the buggies up and down the street, the Amish community in the neighborhood, or we might have goats just being goats. And if we go to the NRC for dairy cattle, National Research Council for dairy cattle, that will be listed as generating requirements for activity. So accounting for the miles they travel, the work they do in some way, shape, or form. So satisfying the nutrient requirements for increased activity. It's usually about extra calories. Yes, there'll be slight increases in nutrients associated with working those muscles, but most of the increase comes in the form of calories. So increased intake to meet those energy needs. We only have a slight increase in increased required nutrients. So generally, because we're dealing with such a large increase of intake, going up faster than the nutrient amounts, we usually have decreased nutrients. The example I gave in class was Michael Phelps. When he was training for the Olympics, they're talking about a 10,000 calories a day that he was eating. And I think there was an interview once with him uh, talking about his diet. And he goes, I can pretty much eat anything I want. Trying to get that many calories in every day, it really doesn't matter what you eat, because most of it's going to be burned as CO2 and water, respired in the body. You can make it protein, fat, carbohydrates, it really doesn't matter. But you get that if you ever started training, usually after the first week, your hunger starts to kick in and you start eating everything in sight. So we have the what the animals do: maintenance, building something, exporting a product, or activity. And then the question becomes, what is the priority for nutrients? And we're going to introduce this concept with Joe's rules. So Joe's rules are from Dr. Joe Domek. He's a professor out at Michigan State University. And he came up with this list of rules. So the first rule for Joe's rules is I will live. So this is equivalent to maintenance. So all nutrients first priority goes to maintenance. So for a lactating dairy cattle, her second priority after she takes care of herself is you'll feed her calf. And that comes in the form of lactation. So we're making milk. The third priority is I will reproduce, or I will create the next generation, if you will. So we want to take care of ourselves first, the calf second, and then if any nutrients are left over, we're going to put them toward reproduction, conception, pregnancy, creating the next generation. So if we look at this and you start to use it out when you're evaluating farms, you have a very elegant system here that, in very simple terms, can show you what's going on a farm. So if we're not getting enough protein, we're not getting enough energy, the first thing that's going to fall is our third priority. If we're really compromised, we're going to lose reproduction and we're going to lose milk production. Hopefully we still have enough in some way, shape, or form for the cow to take care of itself. So Joe's rules. And in my classes, we'll come back to them over and over again. If we take a look, instead of using more of a kind of an elegant but simple view of things, we take a more scientific approach to the priority of nutrients. We will see that maintenance is always, always, always first. And then the other states of being, pregnancy, lactation, growth, and conception, will jockey in priority depending on where they're, what stage of growth they're in, where they are in lactation, and what their energy balance is. So we might put that concept of a limiting nutrient and the priority of nutrients sorted together. You're going to satisfy maintenance first, and then as we have nutrients left over, they're going to go to next priority, next priority, next priority. Once we don't have enough to satisfy the needs, that becomes a limiting nutrient. So you're going to lose those, or have that limiting nutrient in your later priorities, your lower priorities, as we put that together. So thinking about the requirements of a dairy cattle, if we use the NRC dairy, it details 4 states. So maintenance, there are nutrients associated with that. Growth, pregnancy, lactation, there are nutrient needs associated with each one. Algebraically, you figure out the nutrients for each of those things that the cow is doing, if they happen to be doing all 4. And then we add them up. That's the factorial approach toward requirements. Now, are they mutually exclusive? Are they perfectly additive? No, but that's the way mathematically we do and work through. So if we're looking at maintenance, maintenance is always, always first. As an animal grows, now it's going to take priority over pregnancy as she becomes a heifer. So if we're going to get that animal bred, we need to provide enough for growth, enough for pregnancy as we go through. We get to lactation, early lactation. First lactation for a cow, maintenance is going to be first. Growth is going to be second. Lactation is going to be third. And pregnancy will be fourth. If we don't grow our heifers well enough and they have high growth needs, they are not going to have enough energy and other nutrients to produce milk or to get pregnant again. So if animals are doing a lot of growth in that first lactation, you're going to see their lactation curves depressed in some way, shape, or form. As we get toward the end of lactation, lactation becomes less important. Pregnancy might take over. Jockeying there. In the dry period, we're going to have maintenance first. As we get closer to calving, pregnancy is going to take priority over growth. We're not lactating, so that's not part of it. And that pattern tends to repeat over and over again for lactations. So once we have that energy in our feeds, in our body, in the animal's body, where does it go? Where does it end up? And two things we got to check back with are the laws of thermodynamics. So energy can either be created or destroyed. So except on the sun, but on this planet, we take the sun's light and we move it from one place to another. It becomes part of a plant, part of an animal, part of the next generation, part of milk, part of humans, whatever it is. Each step along the way, there's an inefficiency associated with that step. And that gets to our second thing there. The conversion of energy to one form or another is never 100%. And as we lose that energy, we typically lose it in the form of heat. Where does our animal energy come from? Energy of the sunlight is captured in the feed. That's photosynthesis. Feed that's consumed and respired is released to the animal. Respiration. So again, the carbon cycle. When we get to all of the energy in a feed, if we can measure all that energy, is all of it available to the animal? No, it's not. At the end of lecture 10, we introduced this diagram. We'll spend more time on it in 11. So take a look at this diagram that we have our feed. It's got a certain amount of gross energy. It's got digestible energy, metabolizable energy, net energy, and there are certain losses along the way. What we are left at the end, net energy, is what we have available to take care of the cow's needs, maintenance and production. So we'll end it there, and